Welcome to lesson 3.2 on the least squares regression line. What is a general form of a regression equation? It's y hat equals a plus bx, where x is the explanatory variable and y is the response. Y has a hat because it's representing the predicted response that we get when we enter in an x value, because this is just made on a small set of data, and it's also using the linear regression equation, which means it's a line of best fit, and so it doesn't exactly match an actual real life outcome you might get. B is the slope, and you think why isn't this in y equals mx plus b order, where the y-intercept and the bx part are swapped? Well, statisticians like this order, and everybody else in the mathematics field like the other order, so they just split, and statisticians said, well, we'll take this, and everybody else said, we'll take y equals mx plus b, the other order. Anyway, a is still the y-intercept and b is still the slope, where a is the constant, so that's the y-intercept, and the coefficient on the x is your slope. Y hat means it's the predicted value for a given x, and y would have been the actual value of a given x. Okay. Okay, in case you had a different shaped linear regression equation, not linear, but maybe like a quadratic or some other type of regression, it's easier to build more complex equations with this order, a plus bx plus cx squared, and so on, using that pattern, so that's kind of why they came up with this. This will be on the formula sheet, y hat equals b naught plus b1x, kind of the same idea, 0, 1, 2, 3, 4, so on. Okay, but we're just stopping at the linear form. Tapping on cans. Don't you hate it when you open a can of soda and some of the contents spray out of the can? Two AP Statistics students, Carrie and Danielle, wanted to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can has been shaken. For their experiment, they vigorously shook 40 cans of soda and randomly assigned each can to be tapped for 0, 4, 8 or 12 seconds. Then, after opening the can and cleaning up the mess, the students measured the amount of soda left in each can in milliliters. Here's a scatter plot with the least squares regression equation. Soda hat equals 248.6 plus 6.3 per tapping time, milliliters of soda. So here we get the different amounts of tapping times and the different volumes of soda left in the can with a least squares regression line drawn through. Interpret the slope and y-intercept of this regression. Okay, so in the fact of a slope interpretation, you must emphasize the lack of guarantee that as you increase in units of x, that you don't necessarily have to increase in some guaranteed amount of y, and that new points and new predictions should not always lie exactly on this line, that points and predictions will generally follow this line. So for every 1 additional second of time spent tapping the can, the amount of soda left in the can is predicted to increase by about 2.63 milliliters. So it means for each increase in x, there is a slope increase on y. The y-intercept. The predicted amount of soda left in the can is approximately 248.6 milliliters if it isn't tapped at all, 0 seconds. Okay, so we interpret the y-intercept as if it is the ordered pair 248.6 comma 0, and then we just interpret what that would mean. And for slope, we say for each additional 1 unit of x, there's approximately a increase or decrease of about m on the y. Predict the amount of soda remaining in the can if it had been tapped for 10 seconds. Realize that 10 seconds is in between 8 and 12, so it's going to give us exactly what this linear regression gives us, reading across from the 10. And that is when we plug in a 10 in the linear regression equation, we get 274.9 milliliters of soda left in the can. Predict the amount of remaining in the can if the soda had been tapped for 60 seconds, and how confident are you with this prediction? We would get 406.4 milliliters of soda left in the can after tapping for 60 seconds, but this seems weird. We cannot be confident with this answer because we don't know if the linear pattern continues past 12, and true, a can only actually contains 355 milliliters of soda. So of course tapping won't continue to make more and more soda appear in the can. Extrapolation is the use of a regression line for prediction far outside the interval of values of the explanatory x used to obtain the line. Such predictions are not accurate. For example, some data were collected on the weight of male white laboratory rats for the first 25 weeks after its birth. A scatter plot of the weight in grams and time since birth in weeks shows a fairly strong positive linear relationship. The regression equation weight hat equals 100 grams plus 40 grams for each unit of time and models the data very well. What is the slope of the regression line? Explain what it means in the context. Remember that we're saying for each 1 unit of x, there's approximately an m increase or decrease on y. So we're going to say for each 1 week that the rat approximately gains 40 grams per week. So here's just a little summary off to the side just to get our heads in the right place. The slope is 40 grams per week. So here we go. For every additional week of life after birth till week 25, the weight of the rat is predicted to increase by about 40 grams. Real, true, hardcore emphasis on how this is just a prediction and it will gain about 40 grams because we are not saying that each week the rat will gain 40 grams, period. Okay, because that's kind of crazy to think that all rats will gain at the same rate, yada yada. Okay, so make sure that you have a lot of uncertainty in this and not a lot of guarantee. The y-intercept is 100 grams. The predicted weight of the rat at birth, 0 weeks, is about 100 grams. So predict the rat's weight after 16 weeks, we would get a 740 gram rat. And should you use this line to predict the rat's weight after 2 years of age? Use this equation to make a prediction and think about the reasonableness of this result. Okay, so weight hat equals all this. So we would get 4,260 grams when we put 104 weeks in for 2 years. And if we were to convert that to pounds, it'd be 9 pounds. 9.4 pounds is the weight of a large newborn human, which is unreasonable for a rat. This is an example of extrapolation. We cannot assume that the linear pattern continues past 25 weeks. Okay, if something seems like extrapolation, make sure you don't just stop at saying this is an example of extrapolation. Make sure you say that we can't continue using this linear pattern beyond the scope of the data, and give an exact value. A residual is the difference between an observed value of the response variable and the predicted value by the regression line. So what I've been kind of talking about here with this whole predicted and about and the slope is that our linear regression is not actually giving us back, for the most part, an actual data value that actually truly occurred. Many more times, our data deviates from the linear regression line. Okay, and we talked in the last lesson about strength of a linear relationship, and how strong the linear relationship is means how close those points reside to the line. Anyway, so we have all these understandings about this line not exactly going through all the points, but just generalizing that it goes through the middle of all the points. Okay, so with that known, then how much do our points deviate from that line? So what we can talk about is a residual. It's the actual y value minus the predicted y value. So it's basically the difference between the point and the linear regression line. We go observed minus predicted y. When interpreting a residual, you must reference the size and the direction of the error. This rat was 200 grams overweight, okay? That's size, 200 grams, and direction, overweight. The can tapping example. Calculate and interpret the residual for the can that was tapped for 4 seconds and had 260 milliliters of soda remaining. So one thing about this is to figure out, is this your observed or your predicted amount of soda remaining in the can? This sounds like an actual can. Calculate and interpret the residual for the can that was tapped for 4 seconds and had 260 milliliters of soda remaining. Okay? This was a real can. It actually had 260 milliliters of soda remaining, so that's actually a dot right there. Okay? It is not a prediction, although it's very close. Okay, so the prediction would be referring to the line itself. So let's go ahead and label that an observed, so it's a y, not a y hat, it's this one. Okay, predicted is your y hat, and that comes from the equation y hat equals the amount of soda hat is equal to 248.6 plus 2.63 times 4 for 4 seconds of tapping. And all that comes out to 259.12. Very close. Okay. And as we saw, the 260 dot looked like it was just a little bit above that line. All right. So residual equals y minus y hat, which is 260, the original, or the observed, minus 259.12, the amount that the line predicted, okay? And it's 0.88 milliliters. So the can had 0.88 milliliters more soda remaining than we expected. So the size, 0.88 milliliters, and direction, more soda in it. What is a residual's connection with standard deviation and z-scores? A residual, in terms of the y variable, is how far an observation is from the linear regression line. This is similar to the observation's z-score, where a z-score measures the standard deviations from the mean. A residual measures y units from the regression line, which can be considered the mean of all the observations at or near that x value. So they're kind of similar, the idea of a residual or a z-score. Okay, how are the data on some of the McDonald's, or here are the data on some of the McDonald's beef sandwiches. How can we determine the best regression line for this set of data? Okay, so we have carbs and fat. Okay. Okay, so the best line is the least squares regression line is what we would come up with, okay? And calculate the equation of least squares regression line using technology. Make sure to define your variables. So you put carbs on one side, fat on the other, and I go from min to max, and it looks like my lowest amount of carbs is 31, and my largest amount is right around 45. So I just decided to start at 30 and count by twos. And my y's go from about 9 to about 42. So then I just decided to go from about 5 to 45 and count by fives. And then I just plotted my ordered pairs. So 31, 9, 31, 9, and so on. Okay. 33, 12 is the next ordered pair. So 33, 12, put a dot. And I put dots for all the ordered pairs, carbs and fat. And I calculated the least squares regression line. So that meant that in stat edit, I put in L1 all my x's and in L2 all my y's. So here's my data all plugged in, 31 and 9 and 33 and 12 and so on, okay? And then what I'm gonna do to get my least squares regression equation is I'm gonna go stat, calc, linear regression. I'm going to keep going down to option 8, the one that looks like the AP Stats version. And I'm going to make sure that it's saying that my X list was in L1, my Y list was in L2, because that's where I put that. And I'm going to go calculate. Okay. And here I get a lot of decimal places and a lot of accuracy. But here is my A coefficient, or my A constant, and my B coefficient. Okay, so I can substitute those in there. And I can write this out using words so that I'm labeling my variables. Fat grams hat is equal to negative 40.20 plus 1.17 times carb grams. Okay, make sure that you define your variables. If you do y hat equals this plus that x, then below that you'd have to say where y hat equals fat grams and x equals carb grams. So I think it's a little bit less work just to put it right there in words. Interpret the slope and y-intercept. Remember that slope is for each increment unit of x increase of, for each increment unit increase of x, there's approximately a slope m, or b, increase on y. Then we say, for every additional gram of carbs in a McDonald's sandwich, the fat grams are predicted to increase by about 1.17 grams. And the y-intercept is to interpret this as negative 40.20, comma 0 as real world. And so we say the predicted amount of fat in a McDonald's sandwich with 0 grams of carbs is about negative 40.2 grams of fat. This is impossible because sandwiches cannot have negative grams of fat. Calculate and interpret the residual for the Big Mac with 45 grams of carbs. This is 2 points, realize. Calculate, interpret. Okay, so 45 grams of carbs, the residual is observed minus predicted, so it's observed minus predicted. It actually had 29 grams of fat, and we have to calculate the predicted, so we have to put in 45 grams of carbs right here and multiply and add and get negative 36.75, get 36.75 and then subtract observed minus predicted. And we get negative 7.75 grams of fat when we subtract. Okay, so, there it is right there, plugged in. Okay, so in other words, this Big Mac has 7.75 fewer grams of fat than we predicted using the linear model. Okay, all right, let me go back to the calculator here. This R and that R squared are important. R is important to us so far. That's the correlation coefficient. And so 0.74 responds to the, responds to the strength of the linear relationship. And if I hit zoom 9, I can get my scatter plot. And because I originally in stat calc linear regression option 8, because I originally told it to store the regression equation in vars, yvars, function, y1, then it did store that regression equation with all of its detail in my y1 plus 1.17x. Okay. So that's how I got that to show up there. Okay. The least squares regression line that would go through the middle of the points. What was I talking about? Oh yeah. Okay, very good. So R, remember, is the correlation coefficient, and it tells you the strength of the linear relationship. And because the points are quite following the linear pattern, it gave us the R value of 0.72. 0.74. Okay, we're going to get to R squared in a little bit. Okay, if you didn't have R and R squared go on, you can make sure that you turn your diagnostics on by going to second catalog. Okay, and find the least squares regression line by doing these things. Assessing a regression line. All right. How can you know a line is the right model to use? A residual plot is a scatter plot of the residuals against the explanatory variable. They help assess whether the linear model is appropriate. By keeping the x variable the same, I'm keeping my perspective of the points similar. However, I'm going to plot their residuals instead of their original y's. So say that I had these points, and I graphed a line going back to the linear regression equation from each point so that I could kind of show you a visual representation of each point's residual. Now, these have positive residuals that are quite large, and this one has a really small negative residual, a larger negative residual, a little bit smaller, very small negative, and a little bit of a moderate positive residual. So what I did is I took that large residual, I took all the residuals, and I plotted them against a residual line of 0. So a perfect horizontal line here with 0 residual, and I plotted this one, and this moderate one, and this tiny one, and this greater negative one, and this lesser negative one, and this negative one that was just below the line, and then this positive one. And now I just have perspective on just their residuals, just their distances from 0. Okay? Here's another plot and the residual plot. Okay? So here's what I would say. This looked like a clear curved pattern, correct? And when I made it into a residual plot, I can see that pattern magnified. Believe it or not, it is magnified. Now, that helps me see that the linear model was not appropriate because I have a clear positive, negative, positive pattern positive, negative, positive pattern left over in the residual plot. This scatter plot did have a linear pattern, and the residual plot has no leftover pattern. That's a key phrase to use. There is a random scatter in my residual plot. So I have no reason to believe that the original pattern was not linear. So the linear model is appropriate for making predictions in this relationship. The linear model is not appropriate for making predictions in this relationship. Okay, what do you look for in a residual plot? How can you tell if the linear model is appropriate? You look to see if you find a smile, positive, negative, or a frown, which is a negative, positive, or a leftover pattern, okay? Look at the scatter plot, describe the direction, form, and strength, then look at the residual plot for any leftover pattern, okay? Now, if you don't see a leftover pattern in the residual plot, and if the scatter plot looks like it has a strong linear relationship, then you can go ahead and conclude that the line is a good model for the data. If the original scatter plot looks curved and the residual plot confirms a curved pattern, then you can say that the original model was not linear. Now just here's some words on how to describe things. The line, we will refer to it as the model or the linear model. But the actual points in the data plot, where we're going to refer to them as the pattern or the association. Okay, so just an idea of why this works, or why we feel this works to show us a leftover pattern, is if I had a curved relationship and if I subtract a line from it, I would still have a curved relationship. But if I had a linear relationship and I subtract the linear model from it, meaning I subtract all the residuals that from the, meaning I subtract all their distances and find their residuals and plot the residuals, and I'm essentially subtracting a linear pattern from it. So if I have a linear pattern, I subtract a linear pattern, I should be left with no pattern. Okay, so here we go. Here it's kind of written out for you. If the form of the association, which means the dots, is quadratic, and if you subtracted a quadratic from it, then you'd be left with no leftover residual pattern. Okay, if your form is linear and you subtract a linear pattern, or if you subtract a linear model from it, then you're left over with no residual pattern, okay? But if you have a quadratic association in your scatter plot, and you subtract a linear model from it, you're still gonna have a quadratic, okay? So no leftover pattern when you use the correct model for that association. But there is a leftover pattern, a smile or a frown, which means that your model was not appropriate for the association. All right, we cannot use correlation to assess linearity. We've seen high correlation in nonlinear examples, as well as low correlation in linear examples. So remember that correlation alone is not a test for, is my pattern linear? Construct and interpret the residual plot for the McDonald's data. Do the first residual by hand, then use the calculator's resid list. Okay, so what I suggest is we did find one residual for this McDonald's distribution, and we found that it's negative 7.75, so we plot it. I don't know where I plotted it, maybe there. Anyhow, yeah, that looks right. I think it was 45. Okay, so that one right there, the 45 grams of carbs sandwich had a negative 7.75 grams of fat residual. So 45, negative 7.75. And so if we plugged in and we found each residual, that would just take a little while. Sure enough, our calculators are pretty smooth, and they do something in the background. When you go stat calc option 8 linear regression, and you tell it to pull from L1, L2, in the background, the calculator has stored a residual list. It never told you, you never asked it to, it just always does it. Okay, pretty sneaky, right? For the calculator to be doing things and you didn't ask it to do it. So if I go to L3 and I hit enter, this starts to blink, okay? And it's kind of asking me, what do you want to do here? I can go to lists, which I always forget where it is. Lists, yeah, there it is. Okay, one more time. Stat edit, L3 up to it, hit enter, go to second lists. Okay, and then scroll down on every operating system, it's in a little bit of a different spot, but it's somewhere in this first column. There's the word resid. Okay, it might be option 8, option 4, option 10, I don't know. Resid. You want that option though. Click enter. Okay, and you want to go to L3 and put the residuals. Hit enter. I do want that. Now remember what's what. Your L1 is still your x's. Your L3 is now your residuals. So I would like to see a graph, second stat plot, of L1, L3. So I'm going to go second, L3, right down here. All right, and that's how I get my L3 right there. And then graph. Oh yeah, I just need to do a couple more things. I'm going to go to y equals and turn that line off. And I'm going to go zoom 9 one more time so that it fits my residuals. And here's my residual equals 0 line, basically my x-axis. Okay, and all my negative residuals and all my positive residuals. Okay? All right, so there they are, side by side. Okay. S and R squared. In the candy grab activity, we started with only one variable, the number of candies grabbed. To predict how many candies a randomly selected student would grab, we decided it would be easier if we used another variable to help us make that prediction, like hand span, rather than just a mean number of candies. Because we can also just find, well, 10 people have grabbed candies, what's the mean number they've grabbed? So let's just assume everybody else is going to score just about that many candies. Okay. How much better will our predictions be if we use handspan to predict number of candies rather than just the mean number of candies? We can answer this question in two ways, S and R squared.